Okay, so welcome back. Um, the last problem we did, or the last video we did, this little problem with King Kong dropping his 1 kilogram penny off the Empire State Building, and fell a height of 38 or 381 meters. So height was 381 meters. Mass of the penny was 1 kilogram, and we used G equals 10 meters per second squared, and that gave us a final kinetic energy of course, 3,810 joules, and so its velocity when it hit the ground was, I think, 87.3 meters per second. So we solved this problem using energy methods, and that was pretty easy. What I want to put to you now is what happens if, for example, let's say King Kong has a ramp, and he rolls it down a ramp that has an angle of theta with respect to the ground. So the penny rolls down a ramp. What is the penny's speed when it comes off the ramp? Right there. So again, like before, we're going to label this 0, 0.1. So we started doing it the same way we did here. And we know here kinetic energy is, of course, going to be 0 because it starts off, he just lets it go. 0 velocity means 0 kinetic energy. So that's all well and good. So how do we find kinetic energy at 1? Well, that's going to equal the initial kinetic energy, right, plus the work done going from 0 to 1. Okay, so now what's the work done going from here to here? Well, we're going to take the force acting on this thing dotted with delta R. So basically it's going to go from here down to here. So this delta R vector, I'm going to do this in blue here, is going to be roughly like that, right? So it's going to go from this point, or sorry, from this point to this point. I've drawn it a little bit off, but you get the idea. So delta R equals, so here's a little diagram that'll show us what, actually let me draw that a little better angle. Here's a little diagram of delta R. So this is our delta R vector. And vertically, the penny goes, vertically, it's going to go a distance h, right? And it's going to go in the j hat direction. So negative h j hat is this vector, right? And then this vector here, this horizontal part of delta r, is going to be, let's see, so what is this? This is going to be like, oh, let's see, this is adjacent and this is opposite. So adjacent over opposite is cotangent. So this is going to be h cotangent theta times I hat, is this horizontal bit. Okay, so that's lovely. So delta R is h cotangent theta times I hat minus h j hat. That's our delta R vector. Now, what are the forces acting on this thing? Well, on this penny, it's going to be going down the ramp, right? So let's draw the penny here on the ramp with an angle theta. And the penny, like that, it has it's going to be a normal force, right? So let me draw in forces in red. I like to do that, just to keep them separate. And, so this is going to be our normal force here, and that's going to be perpendicular to the surface, of course, and then you're going to have your mg weight there. Okay, so those are the two forces acting. We're ignoring friction, so we're just going to have this thing go straight down. So normal force mg. Now, here's the thing. So the net force on this object is just the sum of all the forces, right? Sum of all forces, right? So, which is going to equal, I'm not actually going to do a free body diagram and all that jazz. I'm going to do this in vector form, and you'll see why in a second. So, again, let's make sure we're clear that we have our x going that way, y going that way. So down here, same thing. Okay. And net force is going to be all this. So this is going to be this normal force vector, and that's going to go, in this direction. And I'll hold off on breaking that down a little because I want to show you something special about that. And then this mg going down, right? So n minus mg j hat. So because this is going in the negative j hat direction. Okay. So that's our net force. Now, work done. And actually, let me do work I'm going to switch to my energy color, which is purple. So, energetic color. Okay, so work is going to mean net force dotted with this delta R vector. Okay, and if we expand this out, net force is going to be, let me see, I got space over there. Okay, is going to be this N minus mg j hat, right, dotted with delta R. Okay, that's all well and good. Now, here's the thing. This is, this is subtraction of two vectors, or addition of one vector and a negative vector, whatever you like to call it. And this is just this is a dot product. This distributes. So we do our distributive property here. Pardon me there, I had to adjust the headset. Okay, so we do our distributive property, and the work is going to be the normal force dotted with delta R, okay, minus mg j hat. Ow, thank you, Sydney. That was my cat getting off my lap. Dotted with delta R. Okay, now, so let's look at these. Delta R is going down the ramp, right? Delta R goes down the ramp. Let's look at this first term, normal force dotted with delta R. If delta R points down the ramp, the normal force points perpendicular to the ramp, remember? So what's the normal force dotted with delta R? Think about it. We've got a vector here. This is our normal force vector. And we've got delta R going downhill. The angle between these two, the angle is a right angle, right? Because these are perpendicular. Delta R is pointing straight down the ramp. Normal force is pointing perpendicular to the ramp. Perpendicular. What's the cosine of a right angle? 0. Which means this whole term, this term here, vanishes. This is all gone. Normal force does not do any work because we are going perpendicular to it all the time. Okay? So we didn't even have to calculate. I mean, we could have broken this down into angles and components and stuff and figured out what it was in components and then dotted that with delta R. So we'd found normal force was some components and dotted those individually, done like the whole component dot product thing with delta R, and then found out it was 0. But if we just step back and think for a bit, we realize, wait a minute, this is going to be 0 anyway. So leave it out. Doesn't matter. Okay? So that just leaves this negative mg j hat dot delta R term. So let's keep going with that. Work is negative mg j hat dotted with, and this delta R term, okay, is going to equal, so what was delta R? We found this up here. H cotangent theta times I hat minus H times J hat. Now, with this vector, this is our force vector, so this is our gravity force vector, because that's the only one that matters now, we've realized that. And this is our delta R vector. We're dotting these two together. Well, we've got this I term here. What's I dot, what do we get if we get dot an I term with a J term? 0. So this also doesn't matter. So all that matters is this negative H times J hat. This dotted with this. And so total work done, believe it or not, is going to be this negative mg here, okay, times this negative H, which means the work done as it rolls down the ramp is going to equal mgh. What was the work done when it fell straight? mgh. What's the work done as it rolls down the ramp? mgh. It's the same. Speed down here is going to be the same as speed here because you're going to get the same work done, so you're going to go from 0. So EK at the bottom is going to equal the same EK at the bottom, whether it rolls down a ramp or whether it falls. Now, the direction it's going is going to be different because when this thing hits the ground, when this penny hits the ground, if it's just dropped, it's going straight vertically, right? When this thing hits the ground, it's going this way, right? So that's going to be a slight difference. So this is going to be our V final there, and here it's going to be going that way. So that's going to be a slight difference. But other than that, it's going to all be the same. It's going to be the same speed, just in a different direction, but it's going to have the same amount of kinetic energy if gravity pulls it down to the ground, no matter what path it takes. Did I say that? Did I say no matter what path it takes? You mean not just for a straight line? That's right. And I'm going to show that to you. I'm going to do one more video and show that to you. That'll be brief, but you'll see that, and I think you'll be very interested.